Hi everyone, in this video I will discuss how I improved the performance of my regression model for predicting medical insurance charges and how I assisted and improved the overall model fit. The dataset includes features such as age, sex, BMI, number of children, smoking status, and region. And the goal is to predict insurance charges as accurately as possible. To improve the performance of my regressor, I first focus on building a robust processing pipeline instead of manually encoding variable. I use a column transformer combined with a pipeline to handle numerical and category feature separately. For numerical variables, I apply median, imputation, and standard scaling. And for category variable, I use most frequent imputation followed by one-hot encoding. This ensured that pre-processing was consistent, prevented data leakage, and made the workflow more productive, production ready. And next, I perform EDA to better understand the relationship between features and the target variable. The correlation analysis showed that smoking status had the strongest positive correlation with charts, followed by age and the BMI, while region and sex has relatively small effects. The visualization, and we can see over here. Oops. And the visualization including bob plots and the scatter plots revealed clear non-linear patterns, especially the dramatic increase in chart for smokers and the upward trend of charts with age. This analysis suggests that linear regression alone might not be sufficient to capture complex relationships in the data. Therefore, I compare multiple models, including linear regression. Over here, linear regression for random forest and X-shape boost. The results show that linear regression achieved an R-square of around 0.81, and while random forest and XGBoost boost both improve performance significantly, with random forest achieved the best validation performance with R squares close to 0.89 and the lowest MSE. This demonstrates that train-based ensemble model has more better suit for capturing nonlinearity and interactions among features. I also performed the basic hyperparameter. Turning increased the number of estimators and adjusting parameters such as minimum sample per leaf for random forest and turning running rate, max dip, and the subsampling parameters for XGBoost. These adjustments help improve stability and reduce overfitting. In addition, I applied fivefold cross-validation to obtain a more variable estimate of model performance. The cross-validation RMSE was consistent with the validation result, indicating that the model generates well and the performance is not dependent on a single random split. To assess and improve model fit, I generate a learning curve for the best performance model, which was random forest. The learning curve shows that as the training set increased, the validation error gradually decreased, and the gap between training and validation error remained moderate. This suggests that the model does not severely overfit and that adding more data could further improve performance. I also examined the feature importance from the forest model, which confirmed that smoking status was by far the most influential predictor, followed by MBI and age, aligning with the earlier exploratory analysis. This consistency increased my confidence that the model is learning meaningful pattern rather than noise. Finally, after selecting random forest as the best model, I retrained it on the full dataset before generating test predictions to maximize the use of variable data. In summary, I improved the performance of my regressor by completing a structured pipeline, conducting through EDA, comparing multiple models, turning hyperparameters, and applying cross-validation. So overall, the model achieves a strong balance between bias and variance, and demonstrates solid predictive performance. Thank you.